Hello, everyone. My name is Alexis OPALSKI, and I'm a rising junior mechanical engineering student at UT Austin. Today, I'll be telling you about my O-REU project, Embodied Intelligence, the Future of Artificial Systems. My sponsors are the online REU program at Texas A&M University, through which I'm doing this project. And I also would like to acknowledge my mentor, Professor Linda Cathey, who's worked by my side and grown my understanding on this project immensely. Now, the concept of intelligence has been around for decades, with many devoted to the understanding of such a controversial and complex theory. It brings about many questions from scientists, all wondering how is it possible that something so sophisticated could have been produced by evolution. By artificial intelligence, we mean the interdisciplinary field that can be broken down into three categories: understanding biological systems, the abstraction of principles of intelligent behavior, and the application of the principles to the design of useful agents. In a more fundamental manner, intelligent systems have the capability of learning. The ability to have cognitive functions and make decisions based on past behavior is what makes systems truly intelligent. Artificial intelligence has evolved from an academic field into a powerful driver force of social and economic change, and will grow into the next era of engineering. When it comes to designing intelligent systems, there is a substantial amount of background information, trying to break it down into simpler parts. The novel Designing Intelligence: Why Brains Aren't Enough, written by Rolf Pfeiffer, Josh Bengard, and Don Barry, dives into the principles of intelligent systems. It discusses the concept of embodiment, why artificial systems must have a body, and how it plays a role in interacting with the environment and its surroundings. It also brings up questions about intelligence versus emotion, the difference between intelligence and cognition, and a lot of other moral questions. Discussing these ethical questions is important to understanding the development and future of the field of AI. Ideas surrounding humanity, bias, security, and privacy come into question and lead to the debate of a technical, analytical, or human holistic approach. Biological systems also provide a comparative analysis of the evolution of learning and memory mechanisms that are crucial to intelligent systems, specifically the octopus. By focusing on brain functions in invertebrates with sophisticated behaviors, we can advance our own understanding of the evolution of the neural processes that mediate such complex behaviors. In recent years, the adaptation of modern neurophysiological methods to the study of the central nervous system of the octopus has allowed for research, and suggests that a convergent evolutionary process has led to the selection of vertebrate-like neural organization and activity-dependent long-term synaptic plasticity. As octopuses and vertebrates are very remote phylogenetically, this convergence suggests the importance of the shared properties for the mediation of learning and memory. In particular, the similarity in architecture and physiological connectivity between the octopus's medial superior frontal lobe/vertical lobe, the mammalian hippocampus, allows for the comparison of features needed to create memory association, crucial to intelligence. We are taking this information and beginning to apply it to engineering systems such as soft robotics. The design and construction of this new class of machines is organized according to the principles of life regulation and must share some essential traits with all living systems. Instead of hardening or adding raw processing power to achieve resilience, these systems are designed instead by introducing vulnerability with soft tissues embedded with electronics, sensors, and actuators, providing a source of information about the body and environment. These machines would have the capability of exhibiting feelings, improving their functionality through various environments, and even developing a conscience. Soft robotics has countless applications, and if we better understand how to design intelligent systems with their own capability of learning, so many advances will be made in technology and medicine. For my project specifically, I had to understand how to design and construct an entirely soft, autonomous robot. Because of our focus on the evolution of the octopus, I also focused my design on what we call the Octobot. The Octobot is a completely soft pneumatic robot with 8 arms powered by monopropellant decomposition. Monopropellant decomposition is when fuel rapidly decomposes into gas by being exposed to a catalyst, which powers the system. The Octobot is controlled by using a microfluidic soft controller created by using a multi-material embedded 3D printing technique. And the overall elastomeric body, which houses everything, is created by a molding technique. As stated before, the Octobot is powered by monopropellant decomposition. Specifically, when a 50% weight of solution aqueous hydrogen peroxide is exposed to a platinum catalyst, a reaction occurs, resulting in volumetric expansion and increasing the decomposition temperature, resulting in combustion. This eliminates the need for external valves to control the gas at high pressures and flow rates. The Octobot is controlled by an embedded soft controller made up of 4 components: the upstream liquid fuel storage, which check valves to maintain fuel flow; the oscillator, which regulates the liquid fuel by a system of pinch and check valves converting the inflow into alternating fuel outflow. The reaction chamber, responsible for the decomposition of the fuel, and the downstream, where gas distribution for actuation and venting occurs. All of these components operate on interaction of time and pressure. A schematic of this control system is shown to the right in the figure. The control logic of the Octobot works as a function of time. First, the nominal pressure drives fuel through the system at a decreasing rate. Then, the pinch valves in the oscillator convert upstream flow into alternating flow. When the upstream pressure is too low, oscillation is not possible, so both sides flow at a reduced rate. Then catalyst decomposes the fuel, resulting in pressurized gas, which flows downstream to the actuators and the vent orifices. Actuators then deform as the pressure changes. This schematic is shown to the right. For the fabrication of the Octobot, the following features are needed: body matrix, fuel reservoirs matrix, printed fuel reservoir traces, fugitive plugs in the soft controller, printed platinum reaction chambers, printed pneumatic networks, printed vent orifices, printed actuators, and mounted hyperelastic actuator matrix. The diagram of this schematic is shown to the right. To fabricate these features, a multi-material embedded 3D printing technique creates pneumatic networks within a molded elastomeric robot body. First, micromold the soft controller that houses the microfluidic logic necessary for controlling the fuel decomposition. A microfluidic soft controller is prefabricated and loaded into the mold. Matrix materials are then poured into the mold. Fugitive and catalytic inks are embed printed into the molded matrix. Then, matrix materials are cross-linked. The aqueous inks auto-evacuate at elevated temperatures as water evaporates and diffuses through the matrix, leaving behind open channels. The Octobot is complete upon removal of excess matrix and material. To create the fuel reservoirs, catalytic reaction chambers, actuator networks, and vent orifices, fugitive and catalytic ink are 3D printed within the molded matrix materials. These printed features are interfaced with each other and the soft controller through fugitive plugs placed at the inlets of the controller before filling the mold with matrix materials. The fugitive ink, composed of pure Pluronic F127, can be auto-evacuated by heating the printed features within the cross-linked silicone-based matrices. The fugitive plugs within the inlet of the soft controller also undergo this auto-evacuation process, connecting the microfluidic logic and the printed components. However, the catalytic ink is cross-linked in place after printing, yielding a platinum-laden plug within the matrix. So that was the overall design and steps needed to create the Octobot. The Octobot is a simple demonstration of the integrated design and fabrication strategy of a fully soft autonomous robot. It serves as the foundation of a new class of soft robots that could provide benefits in manners non-existent before. In the medical field, soft robots have great potential due to their ability to interact with the environment in a vulnerable way. For example, soft robotic intubation. Endotracheal intubation is one of the most common procedures performed in emergency departments and operating rooms. It's a complicated procedure that's susceptible to failure. So I propose the creation of a fully soft autonomous robot that automates this procedure. The soft materials will help reduce risk and damage to the human tissue. It will also increase efficiency in the medical field. Artificial systems and soft robotics are the future of engineering and the future of our world. Thank you for listening to me today.